Hello, chemistry students. Today's video lesson is over standard SC1D, which deals with our average atomic mass and the percent abundance of the element's isotopes. The goal of today's lesson is to, of course, be able to calculate the average atomic mass and also relate the average atomic mass of an element to the percent abundance of one of the isotopes of that particular element. So what is average atomic mass? Well, unlike average in math, where you add up the numbers and divide by the number of numbers, average atomic mass is a weighted average. So we have to take into account the percent abundance of each of the isotopes. The calculation that we do for average atomic mass is going to look different than how you calculate the average for most anything else. Now, traditionally, this is the number that is found on the periodic table if you're given all of the isotopes. The neat thing about the average atomic mass is it is closest to the isotope that has the largest percent abundance. So if more than half of my element is one particular isotope, the average atomic mass of that element is going to be closest to that isotope. Won't necessarily match it exactly, but it will be fairly close to it. Also, the thing to note about average atomic mass is it can't be above the mass of the largest isotope, and it can't be below the mass of the lowest isotope. So if you're getting numbers above or below your isotope ranges, that means you're probably typing something into the calculator incorrectly. So there are several ways to calculate it. I'm giving y'all the most foolproof method for calculating it. If you find another method and it works, as long as you show your calculation, I am a happy chemistry teacher. So the foolproof method of doing this particular calculation, even though we are having percents in the problem, you never ever hit the percent button in the calculator. And we're going to round it always to two numbers after the decimal, mainly because that's what the scales in our physical classroom are able to accommodate. And that is the numbers that most of our masses on our periodic table are rounded to. So how do we calculate it? Well, as I said, we have to take into account the abundance. So what you end up doing is you take the whatever that percent is, again, we're not hitting the percent button, times the mass. So that particular isotope. And then we add. So the key here is that you're adding it. Then we do the next isotope, the percent times its mass, plus third isotope, percent times mass. If there's 4, 5, or 6, we keep repeating this particular pattern until we get all the isotopes and the abundances entered. We get a number, and then we make certain to divide by 100. This fixes it so that you don't have to change any of the numbers into the problem. You're just typing everything that you're given into the calculator. As I said, it is the most foolproof method. If you happen to have one of the Casio calculators, you can actually type it in using the fraction button exactly as you write it on your paper or write it on your screen, and you'll get the correct answer. Now, remember, if you've got that TI, you've got to kind of know the orders of operations, or like I like to say, get a number for the top and then do the divide by 100 for the bottom. So let's look at our first example. This particular example, we've got oxygen, and my first isotope is oxygen 16, and it has a percent abundance of 99.76%. With that large of a percent abundance, that means my average atomic mass is going to be really, really close to 16. The other two isotopes are oxygen 17 with a 0.04% mass, and oxygen 18 with a 0.2% mass. So, like I said, foolproof method. You don't change any of the numbers. You multiply the percent times the mass, and then you add it to the next isotope. So when I go to type this into my calculator, I'm going to have my percent times my mass. And no, it doesn't matter which way you did it. I don't know why I flipped it on this one, but I did. But then I make certain to add the next isotope. So percent times mass, I don't have to change any numbers. Percent times mass, there's only 3 isotopes, so I put them all over 100, and my calculator gives me 15.99, I think it's 6, or 15.997. Well, I said to round it to 2 decimal places, so if I take 15.997 or 6, whichever it is, and I round it to 2 decimal places, that gives me exactly 16.0. Now, AMU stands for atomic mass units. It is how we measure the mass of individual parts of an element. It is based off of carbon-14. Not that we really need to know that, because eventually we're going to get to the point where AMU is going to be just considered grams, because we're going to be thinking of it in terms of a mole of the substance instead of an individual particle of the substance. So what I want you to realize is it doesn't matter if I just give you the isotope or if I actually give you the specific mass of that isotope. So earlier I just gave you the isotope name and we ran with it. Well, in this particular example, we have the full mass in AMUs, atomic mass units. So potassium 39 doesn't actually weigh exactly 39 because protons and neutrons are not exactly 1 AMU. So we are looking at taking these two numbers and multiplying them, taking these two numbers, multiplying them, then adding them together. So my calculation would look something like this. 93.12 times 38.964 plus 6.88 times 40.962, all divided by 100. Remember to add between the two isotopes. So if I did my calculation correct, it should not be below 39. It should not be above 41. And considering that the 39 has the largest percent abundance, it should be really, really close to that. So my handy dandy calculator gives me 39.10146, blah, 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 blah. Don't really care about all that because we're rounding to two numbers after the decimal. So my average atomic mass is 39.10 AMU, atomic mass units. Notice how that mass is really, really close to the one that has the percent abundance. The highest percent abundance is just above because we do have a little bit from the potassium 41. So the next screen has the we do examples. I want you to, once the video pops them up, pause the video, see if you can answer the three questions. Two are calculation and one is just kind of a general question, and then unpause and see how well you did. So question number one is asking, based on this data table, what should the average atomic mass be closest to and why? So this one's set up a little different than what we've seen, but these are my percents. This is the largest percent. So my mass is going to be closest to 56 or 55.9. Why? Well, it's the largest percent abundance. So calculating this average atomic mass, I got 4 isotopes. The calculation does not change. We multiply the percent abundance times its mass. So 5.845 times 53.9. And you guys will notice that I tend to not write multiplication symbols, mainly because I get them mixed up as x's as variables. So I use parentheses, but it's the same thing either way. So my 91.754 times 55.9 plus, I got to add the next isotope. 50, I'm going to try and do them in the same order. It really doesn't matter though. 2.119, that's my percent, times 56.9 plus my last isotope, 0.282 times 57.9, all divided by 100. This fixes it so you don't have to change any of the numbers. My mass should not be below 53.9 and it should not be above 57.9, and it should be really, really close to 55.9. Handy dandy calculator, and I have not pre-calculated this, so bear with me. And hopefully I don't fat finger and hit something I'm not supposed to. Don't forget to divide by that 100, since we're not changing any of the numbers. And my handy dandy calculator gives me 55.80993. Round that to 2 numbers after the decimal. Well, 5 or more raise the score, 4 or less let it rest. I'm going to look at the number right next door to what I want to keep, and since that's a 9, I end up writing 55.81 AMU. If I look at my real periodic table, this is most likely the average atomic mass for iron. So 55.85 is the atomic mass for iron. I got 55.81. That probably means I don't necessarily have all the isotopes, or something has been rounded away, but I can identify what element we just calculated based on what its mass is closest to. So number 3, it's more like what the first one we saw. It's also a lot easier because there's only 2 isotopes. The largest isotope being chlorine-35, so my mass should be closest to 35. I multiply the percent times the isotope mass, my percent abundance times the isotopic mass, plus the other isotope times its mass, all over 100. Again, this is not the only way to do this calculation, but it is the most mistake-proof method of doing this calculation. So my mass should be closest to 35. Well, handy dandy calculator gave me 35.4. Miss Raines is asking for 2 numbers after the decimal, so just add a 0. There's an invisible 0. The calculator just doesn't know it. Notice that that number is really close to 35. So it means we did our calculation correctly. So that is actually it for our new content today. Remember that we're in the meat. If you've got questions over atomic structures, ions, isotopes, figuring out the number of protons, neutrons, electrons, I'm here. I'm available to assist you. I love questions. But this is it for our new stuff for today. Make certain you do attempt the average atomic mass calculations. Y'all won't have very many of them, but I do ask that you actually write what you type into the calculator so I can make certain that you're doing it correctly. And if you don't get the right answer, I can possibly see where you went astray.